Look at this battle scene. We are taking a completely static historical painting and making it move. If you produce video essays or historical documentaries, you know exactly how valuable this kind of fluid B-roll is. Usually, turning a static image like this stone fortress into high-quality video means hitting a paywall. The best AI video generators require an expensive monthly subscription to access their cinematic rendering tools. Today, we are going to build a custom image-to-video workflow inside a platform called Robonio, specifically utilizing the Grok AI model. We are going to set up a system that bypasses the standard usage limits. By the end of this tutorial, you will know exactly how to generate as many of these clips as you need, completely free of charge. Securing high-end visuals for your projects no longer requires a massive budget. It strictly requires knowing how to route your back-end workflow. Step 1 is avoiding the standard browser cookies that track free trials. We need a clean slate, so start by opening an incognito or private browsing window. Open 2 tabs. In the first, load Robonio. In the second, open a temporary email service, like Temp mail. We generate a disposable inbox and copy that address directly into Robonio's registration page. Robonio sends a verification code, but it doesn't appear at the top. You must scroll down to the hidden inbox section where the code actually lands. Paste that code in, and your new account is active. You are immediately credited with 70 free generation tokens. Pairing an isolated browser instance with a disposable email gives you an endless supply of fresh accounts. This is the mechanism that removes the platform's usage caps. Once inside, skip the restrictive basic mode. Click on New Project and select Workflow. This opens an advanced node-based workspace where we customize exactly how the AI processes files. Robonio preloads a default setup that we don't need. Select everything on the canvas and hit Delete. We are starting from absolute zero. First, click the plus icon and add a text section node. This box is where we will type out our exact camera directions and prompt instructions later. Next, add an image-to-video node and connect a line from your text section. Inside, select Grok as your rendering engine. A 5-second video costs 25 credits, but we'll up that to 7 seconds, pulling exactly 35 credits per generation. Deleting the presets and manually wiring these specific nodes together forces the platform to operate exactly how we need it to. We've built a dedicated engine for processing documentary visuals. The architecture is complete. Now we load our raw materials, the historical image, and the instructions on how to move the camera. Click on the image upload section within your node and select your source file. Here, we're loading up our crowded Indian battle scene painting. Now move over to the text section we built earlier. Your prompt means to act like a director's cue. Use specific phrases like zooming camera angle or cinematic slow pan to force the AI into that documentary style. Hit run. Because we selected the 7-second duration, this render will consume 35 credits, exactly half of the 70 we secured at signup. AI video generation is not perfectly reliable. You should expect occasional errors, like warped backgrounds, dissolving geometry, or subjects suddenly growing extra limbs. This is where our setup proves its worth. If the render fails, you have 35 credits left for one immediate retry. If that fails too, you simply close the tab, open a new incognito window, grab a new temp mail, and start again. Software hallucinations aren't a roadblock when your workflow includes an infinite loop. The ability to retry without financial penalty guarantees you will eventually get a usable final clip. Let's look at a successful render. Notice the motion in the horses and the depth added to the warriors. A completely flat painting is now a dynamic moving sequence. The image is clean and highly detailed. More importantly, there are no mandatory logos or watermarks stamped across the screen, which is extremely rare for a free generation tier. You start with your static asset, wire up your custom node workspace, and loop the temp mail registration to render as many variations as you require. With your visuals covered, the next step is layering these clips underneath a clean, synthesized voiceover track to complete a full production pipeline. You don't need studio backing to create premium content. By learning to properly structure your tool, top-tier AI video generation is no longer openly accessible. Foundational models like Grok have locked permanently behind rigid subscription paywalls. For independent creators relying on straightforward chat interfaces to generate assets, this shift severed their production lines overnight. The standard workflow of typing a prompt and retrieving a video is closed. To regain access without the overhead, the current method relies on third-party aggregator workspaces. Platforms like Robonio act as proxies, routing external requests into these gated models. But these aggregators do not operate on simple text inputs. They require users to navigate a visually mapped, node-based scripting architecture. Securing generation time is no longer a matter of writing a clever prompt. It is a structural engineering challenge that requires building a custom pipeline from scratch. The solution to this challenge is a framework we call the ephemeral compute loop. This system operates by linking disposable digital identities with a highly calibrated sequence for image-to-video generation. Executing this sequence forces an alignment across the network. It commands the proxy servers to continuously provision base-level computational power without checking for a paid tier. Standard API routing typically attaches a fee to every second of video rendered. This architecture is designed to bypass those billable events by exploiting the platform's onboarding logic. Mastering the exact routing of this pipeline provides a method for scaling AI production beyond the constraints of a single metered account. We begin the operational phase by isolating the browser environment. Launching an incognito window guarantees a cleared cache, preventing the platform from tracking previous visits. Next, we establish an ephemeral identity. We use a temp mail server to generate a disposable active email address that exists solely for this session. We submit this address directly into the aggregator's registration portal. This initiates the verification handshake required to open the account. The system requires manual intervention. After clearing a CAPTCHA, we switch to the temp mail server, retrieving the numeric verification code to complete the handshake. Confirming that code forces the aggregator to recognize the session, minting a unique user ID. The platform's internal logic automatically seeds every newly verified user ID with an allocation of 70 base generation credits. This authorization sequence functions as the economic engine of the operation. It silently funds the production pipeline before we even upload a single image. Inside the aggregator's workspace, the user interface attempts to steer new accounts toward the beginner-friendly agent canvas. We must bypass this entirely. Our target environment is the pure workflow canvas. This is the only module that exposes the raw node variables we need to manipulate. Upon entering the workflow, the system automatically populates the screen with a preloaded node template, typically designed for basic text-to-image editing. This default graph contains interconnected logic paths that do not serve our specific video generation objective. Leaving them active will cause immediate parameter conflicts. We execute a complete system purge. We highlight the entire web of existing preloaded nodes and delete them, forcibly clearing the interface. Operating within an uncorrupted, blank environment is a strict requirement. Any leftover nodes will drain compute credits or stall the render engine. We start with a completely empty canvas because we are not tweaking a provided template. We are architecting a highly targeted data flow from the ground up. To build the pipeline, we drop in two foundational structural components, a text node and an image-to-video creation node. The text node serves as our sole injection point. It is where we input the behavioral commands and dialogue a model needs to follow. The image-to-video node acts as the central generation engine. It receives the logic from the text injection point and will process those commands against our visual asset. Inside the generation engine is a model selection drop-down menu. Opening this reveals a hidden variable compute cost structure, where different algorithms require distinct amounts of processing power. We select the Grok model. The platform immediately displays its base compute formula. Generating a standard 5-second clip consumes 25 credits. Modifying the requested output duration inside the node alters the internal economy of our pipeline. Extending the generation parameter to 7 seconds scales the compute cost linearly. The system calculates the new requirement at exactly 35 credits. Recognizing this exact ratio is essential. It allows us to mathematically direct our free 70-credit allocation, ensuring maximum output duration with zero wasted processing power. With the architecture built, we require a primary visual asset to begin. In this case, a pre-generated static AI character image. We execute a direct file upload, loading this static image into the waiting image module attached to our video node. Next, we prepare the behavioral prompt. This text string dictates the specific mouth movements, physical gestures, and spoken dialogue we expect the final character to perform. We paste this exact behavioral command string directly into the connected text node, bridging the visual data with our instructions. We initialize the final execution trigger. The nodes lock, linking the injected assets and firing them through the selected Grok parameters. Because this specific request is routed through the aggregator's unmetered free tier API, the platform will intentionally throttle the processing speed. The render will take several minutes. This holding period is the ultimate test of our structural setup. Behind the scenes, the architecture is translating static, disconnected variables into a dynamic computational output. The pipeline delivers the completed render. The immediate value is clear. The system produces a high-fidelity video file entirely free of platform watermarks or restrictive UI overlays. The prompt translated successfully into the generated environment. The character's dialogue maps correctly, and the background features subtle, dynamic animation. However, even with strict node architecture, all current AI models suffer from inherent generative instability. During processing, the model can struggle with complex spatial logic, resulting in visual anomalies. Here, a system hallucination generated a corrupted extra hand merged into the weapon. Because these hallucinations are entirely unpredictable, pulling a perfect render on the first attempt is rare. Running multiple iterations is a mandatory part of the workflow. The output proves that generative algorithms are not flawless tools. Using them effectively requires a robust structural pipeline that absorbs the cost of repeated, necessary failures. To handle those failures, we return to the pipeline mathematics. Each 7-second run consumes exactly 35 credits. Our initial authorization secured 70 credits. That allocation perfectly funds exactly 2 generation attempts before the account balance is drained entirely. Once depleted, we initiate the reset protocol. We manually log out, completely abandoning the exhausted user ID. Then the loop restarts. We generate a fresh ephemeral email, execute a new verification handshake, and rebuild the node architecture on a newly authorized blank canvas. Every pass through this sequence yields another 70 credits. By mastering this architectural loop, creators strip away the financial friction, transforming restricted software into an endlessly scalable, zero-cost production engine.